All right, chemistry, this is your video lecture for chapter 5, section 3. This is the first part of a two-part lecture. We're going to finish up chapter 5 by talking about electron configuration and periodic properties. Things I want you to be able to do in today's part of the lecture. Define the terms group trend and periodic trend. You remember group referring to vertical columns, periods referring to horizontal rows. And then I want you to be able to describe the following term, atomic radius. There is going to be a trend with regard to positioning on the periodic table that has to do with atomic radius, the radius of an atom. You'll need to know what that is. Then identify the group and periodic trends relating to the above term. Okay, up and down, left and right. What happens to the radius of atoms as you go up and down, left and right on the periodic table? We are going to begin introducing the idea of ions in this section. So explain the terms cation and anion. Now in other videos, other people may pronounce that cation. I use the term cation. Either is okay. That's just the pronunciation that I'm going to be using. Then define the terms valence electron. It's going to be a critical term for us for the rest of the course. And then describe the relationship between group numbers and the number of valence electrons in the main group elements. All right, let's get started. So, determination of atomic radius. When we're talking about the radius of an atom, we do not measure one atom by itself. Because remember, what denotes the boundary, the outer boundary of an electron, is the edge of the electron cloud. And as we learned in chapter 4, the electron cloud does not have a hard border. It just simply kind of fades into infinity. So in order to determine the radius of an atom, we actually take half of the distance between nuclei in covalently bonded diatomic molecules. So we're basically taking two atoms, bonding them together, and then measuring the distance between the two nuclei. Okay. So, for example, we can't measure the radius of a hydrogen atom. What we can do is we can take a hydrogen molecule, that's what we mean by diatomic molecule, a hydrogen molecule, which is H2, takes two hydrogen atoms to make one hydrogen molecule, and we can measure the distance between the two nuclei of that hydrogen molecule. Once we know the distance between those two nuclei, we simply take half of that, okay, half of that. That is the radius of an atom. Now the periodic trends with regard to atomic radius, well, that was out of order. Is also known as covalent atomic radii. We haven't gone over covalent bonding, but anytime you see a diatomic molecule like hydrogen, oxygen, nitrogen, things that are N2, O2, H2, that's going to be a covalent bond, and we'll go over why that is next chapter. But for now, it's also known as covalent atomic radii. So the periodic trend, the radius decreases across a period. So as you start on the left side of the periodic table and you move to the right, okay, across a period, the radius decreases, meaning that the atom is actually getting smaller. Now, not only will you have to remember what the trend is, you'll have to be able to remember why. That's due to increased effective nuclear charge due to the increase in positive charge. And what that means is as you go across a period from left to right, you're increasing the number of protons in the nucleus of the atom you're looking at. For example, as you go, from lithium to, say, boron or anything to the right in that period, you're successively adding one proton. Well, if you're adding one proton, you're increasing the amount of positive charge. And if you're increasing the amount of positive charge, you're also increasing the pull on the negatively charged electrons that are in the electron cloud, because remember, opposite charges attract. Opposite charges attract. And so if you increase the amount of positive charge, you're increasing the pull on anything that's negative in the vicinity, and that would be the electron cloud. So if we're pulling the electrons closer in towards the nucleus, we're making the electron cloud smaller. Okay, we're making the electron cloud smaller, therefore decreasing the radius of an atom. So that was the period trend. Now let's talk about the group trend. As you go down a group, right, from the top of the periodic table down, we're actually going to see the radius of atoms increase. And this is actually going to be a lot simpler to describe. The reason that they increase as you go down a group is because you're adding a principal quantum level, right? N goes up every time you go down in a group, right? N equals 1, N equals 2, N equals 3, N equals 4. Remember what a principal quantum level is. It's an energy level. You're adding another shell around the nucleus, making that atom larger. Sweet, sweet sound effect. This is a graph picturing atomic radius and its trends, and you can see that if you're looking at the period trend, you start with lithium, then you go over to beryllium, to boron, to carbon, to nitrogen, oxygen, and fluorine. You're actually seeing as you go to the right, these atoms are getting smaller. But as you start in any of the groups and you go down, they're getting larger. So please pay attention to this graph, this picture when you are studying for your quiz. Now, we're going to start talking about ionization energy, which is the next trend we're going to talk about. But before we do that, we need to understand what ionization is. And in order to do that, we need to understand what an ion is. In order to do that, we need to understand why you would form an ion in the first place. So strap in, here we go. We want to be able to achieve an octet because, like we've talked about in the past with regard to noble gases, atoms want to have 8 valence electrons. They want to have 8 outer electrons. Now, the reason that is, it results in stability. Okay, it results in this perfect stability, not perfect, but the best natural configuration that you can find is the noble gas configuration, and that is having 8 valence electrons. Now, as we have practiced doing, trying to calculate how many electrons a particular atom has, not all atoms will have 8 valence electrons normally. In fact, if you're not a noble gas, you don't have 8 valence electrons normally in the electrically neutral state. But atoms, they want to have 8 valence electrons. So in order to do that, they will either lose electrons or gain electrons in order to acquire that noble gas configuration. And whether or not they gain or lose electrons has to do with where they are on the periodic table. Meaning how many valence electrons they do in fact start with. Okay. Again, here we have our definitions: cation and anion. Cation is a positively charged ion, okay, and an anion is a negatively charged ion. We're going to use that for the rest of the course, so please be sure to nail those down. And the reason this is going to be pretty important for us because, remember, opposites attract. So once we make a positively charged cation and a negatively charged anion, these things are going to attract one another, and that's going to help us out when we start learning about ionic bonding next chapter. But back to the idea of ionization energy, we need to achieve an octet. So in order to accomplish that, we are going to either gain electrons or lose electrons until we have that full 8 valence electrons in our outer shell. So we can predict this. Metals, remember, if you have your periodic table out, metals are on the left side of the periodic table. Non-metals are on the right. You see that metals tend to lose electrons because they don't have very many valence electrons in that outer shell. They're going to have less than 4. Or should I say 4 or less. They're going to form cations because they're losing electrons. Remember, electrons are negatively charged, and if you're losing electrons, that's like subtracting a negative number. Okay? You're actually going to yield a positive charge. For example, sodium, you guys can do this. Sodium's electron configuration is 1s2, 2s2, 2p6, 3s1. You can see it's in the 3rd row. It's in the first group, so that makes its outer shell 3s1. That means it has 1 electron in that 3rd energy level. Well, if we were to just lose that last electron, get rid of it, the highest occupied energy level would be n equals 2. Well, guess what? We have 2s2 and 2p6. That's 8 electrons in n equals 2. That would give us 8 valence electrons, and that would give us a stable configuration. So sodium is going to lose, is going to eject, send away that 3s1 electron, and it will be sodium plus 1. It's going to be a sodium ion, and it will now have the electron configuration of 1s2, 2s2, 2p6. And it will now have the exact same electron configuration as neon. Now, don't mistake this for a change in the number of protons. Okay, the number of protons isn't changing. We're just talking about losing electrons. Now, nonmetals are going to do the opposite. Nonmetals tend to have more than 4 valence electrons. So it's actually easier to get to 8 by adding electrons. So, for example, oxygen, we can find the electron configuration for oxygen. It's 1s2, 2s2, 2p4. If we gain 2 electrons, we'll fill up that 2p orbital. So we'll now have 8 electrons in n equals 2. That'll give us 8 valence electrons. A full octet will be stable. Well, with the addition of 2 electrons, that oxygen now becomes negatively charged. In fact, it has a -2 charge because it's gained 2 electrons. It's now considered an anion. So, electron transfer, anions. When an atom gains electrons, it increases its negative charge, so it becomes negatively charged. There are now more electrons than protons, and you can figure out exactly what the charge of an atom is. For example, let's look at nitrogen here. Nitrogen's number 7, atomic number 7, so it has 7 protons, and it normally has, if it's electrically neutral, it has 7 electrons. But here's the thing. That's not a noble gas configuration. It's not a stable configuration with 8 valence electrons. Nitrogen is actually going to gain 3 electrons, so it can get to the electron configuration of neon, which is its closest noble gas neighbor. But by gaining 3 electrons, it has a -3 charge. Again, that's the difference between the number of protons and electrons. Let's look at the same process, but with cations. When atoms are losing electrons, they're losing negative charge. They become positively charged. And we have now more protons than electrons. So potassium, number 19, if it's going to be neutral, it would have 19 electrons as well. But in order to reach that noble gas configuration, potassium is going to go backwards to argon, and it's going to have 18 valence electrons. That'll give it 8 in that outer shell. It'll be nice and happy and stable, but it'll now have 1 more proton than electrons, giving it a total overall charge of +1. All right, guys, we're going to leave off right there. We'll start next lecture finally talking about ionization energy. You're definitely going to need to have a handle on this idea of ionization. Okay, either gaining or losing valence electrons in order to gain that noble gas configuration. So don't sleep on this one, because if you do, next lecture will make no sense to you. All right, guys, I will see you next period.